Now that we've seen some examples of polar and radical reactions, we are going to dig a little bit deeper into reaction details. In this video, we will be looking at thermodynamics of organic reactions. With thermodynamics, we focus on reactions at equilibrium. So many reactions, we can think of them as going from reactants toward products. But in addition, many reactions will also proceed where the products will revert back to form the reactants. Eventually, when the rate of the forward direction is equal to the rate of the reverse direction, that system is at equilibrium. So equilibrium is a state in which the rate of the forward reaction is equal to the rate of the reverse reaction. So equilibrium is the state in which the rate of the forward reaction is equal to the rate of the reverse reaction. Now, because this is an equilibrium state, normally we want to think about what actually exists at equilibrium. So does the reaction occur to a significant extent the way that it's written from reactants to products, or does it actually occur more so in the reverse direction from products to reactants? So let's take a look at a generic example of a reaction. And for an equilibrium reaction, we would write our arrows like this. So this is an equilibrium reaction. So capital A reacts with capital B to form capital C plus capital D. The lowercase letters, these are the coefficients that clarify the stoichiometry. Now for any equilibrium reaction, we can define an equilibrium constant, which is given by a capital K, where this equilibrium constant is equal to the concentration of products raised to the power of their coefficient, divided by the concentration of the reactants raised to the power of their coefficients. So if this is a 1-to-1 to 1-to-1, then we just have K equals CD divided by AB. Now, what does the equilibrium constant tell us about the position of equilibrium? Well, if, for example, the equilibrium constant K is much larger than 1, to get that mathematically, that means our numerator is bigger than our denominator, which means we have more products than reactants. In other words, this equilibrium lies to the right as it's written. On the other hand, if K is less than 1, we would get that in a case where the numerator is smaller and the denominator is larger, which means we have more reactants than we do products. Or we would say that the equilibrium lies to the left. Now, the equilibrium constant K can be quite large or quite small, so often scientific notation would be used. Now, if we have an equilibrium constant, say on the order of 10 to the third, that means we have a lot of product, and in that case, our reactant is barely detectable. So I just want you to have kind of an idea about what this means in terms of the position of equilibrium, what is the equilibrium constant K, and what does that tell us about what exists at equilibrium. So remember, we are writing our equilibrium arrows like this. This tells us that the reaction occurs in the forward direction and in the reverse direction. At equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction, but it is not necessarily the case that the concentrations of reactants are equal to the concentrations of the products. That is not equilibrium, but instead the magnitude of the equilibrium constant gives us information on whether we have lots of products or whether we have lots of reactants. Now, at this point, you should be asking why. Why do certain reactions have an equilibrium expression where the equilibrium constant is greater than 1? Why are some less than 1? And this is what we talk about when we're thinking about thermodynamics. As we consider thermodynamics, we want to focus on the Gibbs free energy change, which is given by delta G. So this is calculated as the Gibbs free energy of the products minus the Gibbs free energy of the reactants. For a favorable equilibrium, energy must be released. So imagine a favorable equilibrium would be like a rock rolling down a hill, and an unfavorable equilibrium would be like trying to get a rock to roll up a hill. So if our product is low energy, more stable, and if our reactants are high energy, less stable, then that is going to give us a favorable equilibrium because we have a negative delta G. So that would be an example of an exergonic reaction. So this is a negative delta G, which means that there is energy lost by the system or energy released by the system. And usually that energy is released as heat. In contrast, we can have an endergonic reaction, which has a positive delta G, and here energy must be absorbed by the system. In addition to delta G, we often focus on delta G0, which refers to the delta G at the standard state, which refers to a compound or element in its pure stable form at 25 degrees Celsius and 1 atmosphere of pressure. So for the most part, that's what we're going to be focusing on. If I say delta G, I really refer to delta G0. So a negative delta G means it is a favorable reaction. A positive delta G means it's not favorable, so we would have to put some energy in to get the reaction to go. Now, another common way to refer to this, if we have a negative delta G, then this is a spontaneous reaction. It's a favorable reaction because it is spontaneous, or it is spontaneous because it is a favorable reaction. Therefore, an endergonic reaction, one that has a positive delta G, this is non-spontaneous. And we would have to force the reaction to occur by giving it some kind of energy. So spontaneous versus non-spontaneous reactions. Now, what are the components of delta G? What determines whether the delta G is positive or negative? Let's take a look at that. The Gibbs free energy, or delta G, is equal to delta H minus T delta S. The delta H is the enthalpy change, and the delta H is known as the heat of reaction. Basically, this is determined by the differences in bonding energies. So when we're going from A plus B to form C plus D, we have to break certain bonds in A and B, and we have to form certain bonds in C and D. And so the bond breaking, bond forming, that difference in energy is what determines the heat of reaction, or the delta H. For an exothermic reaction, this means we have a negative delta H. The products are more stable. They are lower energy, and there are stronger bonds for an exothermic reaction. For an endothermic reaction, this would be a positive delta H. So here, the products are less stable or higher energy and overall weaker bonds. Delta G equals delta H minus T delta S. T is the temperature in Kelvin. And what about delta S? Delta S is the entropy change, where entropy is a measure of disorder. Now, if a system becomes more disordered, then we have a positive value for delta S. If a system becomes ordered, then we have a negative value for delta S. So we gain entropy when we gain disorder. In real life, this is when your room gets messy, your office desk gets messy. In terms of reactions, one way to think about entropy, one way to think about disorder is the idea of the number of molecules. If we are going from one molecule to two, then there are more possible arrangements for these two molecules to be, and so the products would be more disordered than the reactants. Now, on the previous slide, we said that for a favorable reaction, we would have delta G as a negative value. So that means we want our delta H to be negative, and then because it's minus T delta S, we want our delta S to be positive. Now, it's possible to have a reaction that's very exothermic, so we have a really big negative delta H, so that even if our entropy is negative, then overall this term doesn't outweigh this term. For many organic reactions, the entropy change is not as significant as the bonding energy changes. Of course, we're going to come across some exceptions, but for most organic reactions, we are going to focus on the delta H term, the enthalpy of reaction. Now, whether a reaction is favorable depends on the delta G, and the delta G depends for many organic reactions primarily on the delta H. And the delta H is really determined by the relative bond strength of the reactants compared to the products. So how do we get information on bond strength? One way is to use information on bond dissociation energies. Let's consider, for example, a molecule AB. We can measure how much energy is required to break this AB bond to give us an A radical and a B radical. Now, because the bond dissociation energies are measured as a radical reaction, what does that mean for polar reactions? So the BDEs, the bond dissociation energies, give a measure of the bond strength, and this bond strength can be applied to either radical or polar reactions. This is a table from your book, and we have some bond dissociation energies given in kilojoules per mole. So let's look, for example, at HF compared to HCl, HBr, HI. We made a comparison between these molecules when we were talking about relative acidity. As we go down the periodic table, the acidity increases, and you can see that the bond strength decreases. So it's easier to break the HI bond than it is to break the HF bond, which means HI is more likely to act as an acid than HF. If we look here again at the halogens, so we have a methyl group connected to chlorine, connected to bromine, connected to iodine. And to break this bond, that requires 350 kilojoules per mole. To break the carbon iodine bond, that requires only 239 kilojoules per mole. So by looking at the bond dissociation energies, what we see is that in terms of bond strength, an alkyl group connected to a chlorine is stronger than the carbon bromine bond, which is stronger than the carbon iodine bond. And we're going to see how this is very, very important regarding reactivity. Now, it is possible to use bond dissociation energies to calculate the delta H for a particular reaction. There's a lot of information that can be determined using bond dissociation energies. And if you want more information on this, you should take a look at any general chemistry textbook. We started this video talking about reactions at equilibrium, and then we've been talking about free energy and the different components of free energy. So let's get back to thinking about the relationship between free energy and the position of equilibrium. So there is another pair of equations that we need to use. We know that delta G is equal to delta H minus T delta S, but delta G is also equal to minus RT times the ln of the KEQ, so the equilibrium constant. So R is the gas constant, 8.314 joules per Kelvin per mole, or this can be in calories. T is the temperature in Kelvin. Ln is the natural log rather than the logarithm. This is the natural log where E equals 2.718. This is a button on your calculator that you can punch in. Let's take a closer look at this equation. So delta G equals minus RT times the ln of capital K. If we divide both sides by negative RT, then we get delta G over RT, where this is negative, is equal to the ln, the natural log of the equilibrium constant K. Now we want to take the inverse of the natural log of both sides. So the inverse natural log of the right side just gives us K. The inverse of the natural log of the left side gives us E raised to the power of negative delta G over RT. So that gives us this equation over here. So from this, you can see that the equilibrium constant, which we already defined as the concentration of the products divided by the concentration of reactants, this equilibrium constant can be calculated based on the delta G. Now let's take a look at a sample reaction, and this is what we looked at earlier in the chapter. If we have an alkene and it reacts with HBr to form an alkyl bromide. This is an addition reaction. Now, if we could measure the concentrations of our reactants and products at equilibrium, then we could calculate the equilibrium constant K. So let's say for this one, we determine that the equilibrium constant K is 7.1 times 10 to the 7. Let's plug that in to this equation. So if this is our value for K, then the natural log of K is equal to 18.08. So our delta G is equal to negative R. Let's do 8.314, and notice this is in joules per Kelvin per mole. If this reaction is done at 25 degrees Celsius, that is 298 K. And then we plug in the ln of K is 18.08. And so that should give us a value of approximately negative 44,800 joules per mole, or we could say that the delta G is negative 44.8 kilojoules per mole. So because the delta G is negative, we know that this is a favorable reaction. And starting with the equilibrium constant, we can calculate the delta G. Alternatively, we could start with the delta G. So if the delta G is negative 44.8 kilojoules per mole, let's convert that to joules per mole because our other terms are in joules. So we have negative 44,800 joules per mole. So then if we use our expression for the KEQ is equal to E raised to the power of the negative of negative 44,800 divided by R is 8.314 and T is again 298. So we take this, we divide by these numbers, take the negative, and then we take the inverse of the natural log, and that should come out to an equilibrium constant value of about 7.13 times 10 to the 7th. So it's helpful to try out some of the calculations. Now, what does this mean then for the delta G in terms of its components of delta H and T delta S? Well, we're going from 2 molecules to 1 molecule, so there is a decrease in the entropy. So the delta S would be negative, and so T delta S, a negative T delta S, would then be positive. So that's not helping much as we're thinking about our delta G. But let's think about our delta H. We need to break a pi bond and break a sigma bond. We form a sigma bond and another sigma bond. Sigma bonds are stronger than pi bonds, so that means that overall we have stronger bonds in our products, and so we're going to have a favorable delta H, which will have a negative value, and so that makes sense with having the negative delta G. So mathematically, I want you to be able to use these different equations to be able to calculate the equilibrium constant from the delta G, to be able to calculate the delta G from the equilibrium constant, or to be able to calculate the equilibrium constant starting with the delta H and delta S and knowing what the temperature is. So there's a lot that can be done mathematically to be able to figure out the details of any particular reaction. I forgot, we could also use the bond dissociation energies to calculate the delta H, which could then be used to calculate the delta G, which could then be used to determine the equilibrium constant, which could be used to determine the position of equilibrium. How much of our reactants versus products do we have at equilibrium? So these are not the types of calculations I'm going to give you to do all the time, but I want you to have an understanding of that conceptually, of how a piece of information can feed into other information.